Right, okay, we'll do this one. Mathematical induction. So in mathematical induction, what is mathematical induction is, there is a process. Okay, mathematical induction is a process to verify the given statement, if the given mathematical statement is true or not. Okay, so mathematical induction is a process to verify whether it's true or not, right? The given mathematical statement is right. For an example, one person came up with, okay, so if you add 1 plus 2 plus 3 up to n, so it's going to be n by 2 into n plus 1. So if a person says something like that, okay, and especially there is a what we learn in the mathematical induction, our syllabus is easier, right? Okay, so there are others type of mathematical induction also, right? Okay, so here 1 to 2, then so what we learn is only for n belongs to z plus. Okay, so what we learn here, positive integers. Okay, positive integers. So if n belongs to positive integers, right, then only this is all the positive integers. So all the positive integers related statement, mathematical statement, we can verify using the mathematical induction. So there is a process. I'll tell you what is that. Okay. So what do you mean by n belongs to Z? So for an example, so if anyone come up with a statement like this, okay, how you are going to verify this is true or not? Okay, is it true or not? So then you don't know actually, because what we have to do, okay, you have to put the values for n and check. So that person says this is true for n belongs to Z plus for all the values of n. So for all the values of n belongs to Z plus. That means the positive integers. So n can be any positive integer. So he says this is true. So now you have to verify that. So how to verify? Using the mathematical induction. So if you don't have the mathematical induction, what you can do means you have to put the values and check. Say put n equals 1. So 1 is here. Here 1. Okay, so you will find it. If you put n equals 2, then you will get 1 plus 2, right? That is n equals 2 means 1 plus 2. So you will get the same. So 1 plus 2 is 3 if you put there 3. So if you put 3, 1 plus 2 plus 3, right? So how long we are going to put? So 4, 5, 6, 10,000 numbers, infinity numbers, you can't do that. And we don't know, it may be wrong after a certain number, right? This may be wrong after a certain number. We don't know. So we may assume that this is okay, correct. We don't know. This may be correct only for the few numbers. We don't know. So for an example, if I say something like that, 2 to the power n, so n factorial, right? 2 to the power n and n factorial. So in that case, if I say 2 to the power n factorial greater, less than or equal to something like that. So this is the statement. I came up with the statement. I say n belongs to any positive. This is true. So what you will do? You will check by putting n equals 1. So here 2. This is wrong. No? Other way wrong. Okay. So you may think other way wrong. Okay. So 2. Here 1. Correct. If you put n equals 0, this is 1. This is 1. 0 factorial 1. So that should be greater than or less. Okay. 0 factorial 0 greater than equal 1. Okay. So but if you put n equals 2, so you say 4. This is 2 factorial, that is 2. Okay, that is also correct. For n is equal to 1, correct, 2 is correct. If you put n equals 3, 8. 3 factorial, 3 into 2 into 1, 6. So that is also correct. So we are happy. If you put n equals 4, 16. 4 factorial is 24. This is wrong. Okay. Now, what do you think? So we don't know. After here, we found after 4 numbers. Okay. So we don't know. We can find anything after infinity numbers, right? So there is a problem. So always mathematics we never accept without without proper working, right? So proper proof, right? So if anyone come up with any results, so we have to verify whether it's true or not. So that is challenging now because anyone can say something like that. So I don't know. I may believe first by putting first 3 numbers. Okay, yeah, he's correct. Okay, well, he's the best man. No, not like that. So this is wrong. When you put n equals 4, this is 16. This is 4 factorial. It's 24. This is the other way around, right? It goes. So there are things like that. So these things, how to verify that? Okay, how to verify? Actually, what we learn is in our syllabus in positive integers. That is the thing. Okay. So how to verify these kind of things? So this is the challenge what we have. So we made a process. There is a process how to verify. So that process says, okay, so what we are trying to do is we are trying to put 1, 2, 3, 4, n. So what we are doing, so we are consecutive things, we are consecutive numbers we are putting for n. So, okay, so consecutive, okay, what do you mean by consecutive? So can you write mathematical notation for consecutive numbers? Yes. So consecutive numbers means n, n plus 1, n plus 2. So this is we call consecutive numbers. Okay. If you put values for n, so you will get consecutive numbers. Okay. Then, okay, you can turn that to the mathematical notation. Okay. So how to verify, how to write a process to verify these kind of statements. So then we decided to see there is a, okay, there is a book track or cycles. You know the cycles in all days. Uh, the cycles they park like here. So these are the cycles. They park like here. So have a, having a certain interval, right? So the cycle. So if you just push this cycle, what will have bicycle? What will happen? So everything will fall. You know that. So or I'll explain through the bookshelf. Okay. So you can see bookshelf. So that's a very good example rather than cycle. Cycles only we see in the we don't see it here, Colombo, but other cities we can see. But here we can assume there is a bookshelf. Okay, so there is a bookshelf. Okay, there is a bookshelf. So the books are here. So this is one book. Okay, there is another book. There is another book. All are same, similar, or identical. Identical books. Identical books are there. Identical books are there. What I'm trying to say is this gap is less than this height. This gap is less than this height. So if I push one book, will you say the last book, the final, the last book, will it fall? Will it fall? So I'm asking you, tell me, tell me, if I if I push this, if I push this first book, will the last book fall? Yes or no? If I push this book, will the last book fall? Yes or no? Tell me. Yes, how? Because this will hit here, so this will fall. This will hit this one, and likewise. So this is a consecutive progress, right? Right. This is a natural progress, right? So how we are thinking how to, okay, so this is a natural process, how to tell in mathematical way. So this process is there. So I have to convert this process to the mathematical way. So that is what we are doing actually. Indirectly, we don't know many cases in applied maths also we do that one. So we drop a ball. Drop a ball is a natural thing. Okay. So natural motion, like if you drop a ball, it comes down. So mathematically, we can explain that motion using the v equal u plus at or s equal u plus half at square or v square equal u square plus so many equations. So if v equals m means so many equations, right? So that is mathematical process. Likewise, here the process is the natural process is if natural process, what I need to know, the if a book falls, then the next book also will fall. What's that? If there is a condition, if the book falls. So if I'll say this is the first book, this is the first book. This may be the nth book. Okay, this may be the nth book. So I'll randomly I say there is a kth book or fifth book or art book. Art book is we know that because R is the common term, no? Same way, yeah. The series we have learned. Okay, like we can use the K, right? So some students they use the P. There's no don't worry. We use K. Okay, K book. So think about the K book. Okay, so I'm asking if K book falls, right? If K book falls, what will happen to the K plus one book? Definitely it will fall, right? If we can prove that, okay, so this now I'm converting the mathematical things. The first one, that is a natural thing. That is mean if I push the first book, I know definitely the book will fall. So if I put the okay, so then mathematically I need to say consecutive books are falling. So what is that? How if any way, if any kind of things I can express in mathematical way, the consecutive books are falling or consecutive books are falling. So how to convert that natural process, consecutive books are falling, so that natural process to the mathematical way, that is the way. If you can show that kth book, if kth book falls, uh, okay, then K plus one book also falling means we are proving consecutive books are falling. Right? Is it clear? In naturally, consecutive books are falling means how can be converted to the mathematical way? So if K book is falling, K plus 1 also falling. So because of the K book falling, K plus 1 falling. If I can prove that, then I'm proving the consecutive books are falling because K can take any value. If you put 1, 2, 1, 2. So 1 falls, 2 falls, 2 will fall. If you put 2, 2, if 2 falls, then 3 will fall. Like that, consecutives. Okay. So then we decided, this is the process. Okay. So I need to prove, yeah, I need to take that K is falling. Okay. I need to take K is falling. I need to assume that K is falling, K book falling. Then I need to show, if I can show that because of that K plus one book also falling means, then this process is true until the end. But it can be happen like this. I can push the middle book. Okay, maybe a book in between this. And I can say this here falling. So that doesn't mean everything falling, isn't it? So I can push a book in the middle of this bookshelf, right? So like this, then I know that from that up to end, all the books will fall. But before that, no. So that's why I need to say the whole process is true. Then I have to examine. I have to push the first book also. So I have to prove that n equals 1 also true. And we have first of all I have to prove that the first book. If I push the first book, will this book fall? Okay, I have to prove that. Okay, and then I prove the process. If I push a kth book and kth plus one book also falling means now I can say entire book will fall because I know the first book also falling. I know consecutive books are falling. Then you can fix that consecutive things 1, 2, or 2, 3, or 3, 4, or like this up to n. So all will fall. So this is the process what we developed to ensure or verify the mathematical truth when n is positive integers only. When n is a positive integers only, right? So that is in our syllabus mathematical induction. So if you learn go the university, you will find many mathematical inductions. There are many. Okay, right. Okay, so this is the process. Okay, so what you can do is just mathematical induction, put the heading. Okay, so draw this. Actually, it's better to draw this. This is the first book. Say this is the first book, and this gap is same. say this is a Kate book, and say this is a K plus 1 book. So K plus 1 book. Okay. So if Kate book falls, right now, K plus 1 book also falling. Also falls, right? Okay. If Kate book falls, K plus 1 book also falls. And the first book falls, then we can prove that entire books fall up to n. This mathematical process, is mathematical induction. Is it clear? Normally, mathematical induction means they start with 1 plus 2 plus n, prove this n equals 1, n equals k plus 1. You have to do that. But you need to know the concept behind that, how they develop the mathematical induction. Because of this natural process, right? That's it. Mathematical process is mathematical induction. So, that is, let me put the heading, format of the mathematical induction. Format of mathematical induction. Format of mathematical induction. Format of mathematical induction. We will do this. And it is this one. Format of mathematical induction. Write down the format. Then what is the format of mathematical induction? So statements will be given. That means mathematical statement. This is equal to that or something like that. So we'll write statement. Quickly write that. Statement 1 equals statement 2. So the process, the first one, we have to prove for n equals 1. So for n equals 1, you have to take LHS. And you have to prove, you have to simplify. I erase this. And you have to say eventually, this is something else. Say you have to say LHS equals RHS. If it's equal, then equal. If it's inequality, then inequality. So I erase this one. Hope you are writing. So you have to say this is true for n equals 1. That means you have proved that the first book is falling. So now you have to prove that consecutive books are falling. So then that means that consecutive can fix any place up to n. So you can say all the books are falling. So I erase this. Okay. N equals 1. So I erase everything. So this is true for n equals 1. So now you have to take, let this is true for n equals k. So then you have substitute there. Statement, we will do one example with k. Okay, that equals statements 2 with k. So you have to substitute. It's always, earlier it was in n, so you substitute with a k. So you have to assume that this is true. First of all, you have to take that is okay, this is true. Then we'll examine that. So then you have to do something else, we will tell you. And after that, we have to prove that. Okay, so up to now, it's okay. So this is a format that we are going to follow, the mathematical induction. So copy this, statement 1, statement 2. After the process, put dot, dot, dot. So we will prove that statement 1, k plus 1, by putting k plus 1 equals statement 2k plus 1. So this is true. We will prove that at the end. So that means instead of k, if you put k plus 1, if that remains like the same thing, so we can say this is it is for all the values of n, all the positive integers of n, the statements are true. Okay, so that is the last. There is a small uh, paragraph you have to write that I'll tell you later. Okay, so there's a small paragraph you have to write, I'll tell you later. So now mathematical induction example, the best example ever. Before we go to the examples, so the map, we go to the map, how many types questions are there? The mathematical induction, there are 4. 1, 2, 3, 4. There are 4 types mapping. So in the map, I can say mathematical induction. The first one, series type question. So series type question. So that's why you need to learn the series before you learn the mathematical induction. Because otherwise, what happens, if you learn the series, if you learn mathematical induction before series, when you are learning, then you have to teach the series by what is the meaning of sigma, and what is UR, what is this, what is the next term, how we are adding. So rather than struggling there, it is better to learn the series, then the mathematical induction. So then no problem. So if I say sigma r square, then equal n by 6 and n plus 1 into n plus 1, then you won't worry about that. We know that. Second one is division type. Division type. So that's all. So after 2000, maybe, yes. After 2001, so therefore after 2001, for 20 years, we are having only sharing this series type or division types. There are no other types after 20. So this 20 years, we are having series type or division type. So it may be series type, it may be division type. So this is 60%, this is 40%, like that. Okay, but there are another two types, but we had one other term on two past paper we had, that is, 2002 and 2003, that is inequality type. So I put in red because they may put inequality type. And the finally, they go with this equation type. Equation type. Okay, so that when we go through the questions, we will learn. Sometime, first time we take n equals k and we have to put a k plus 1. Some question we have to take both k, comma, k minus 1. We have to take this true and we have to prove that for k plus 1. So some cases are like that. Okay, so mathematical induction is the easiest. but according to the question and according to the theory what we have learned. Okay, so these are the uh, things that you need to focus on. Mathematical inductions, there are 4 types. So we are sharing 60% and 40% here. New syllabus is like that. So the first part is coming, the first question you are meeting as the first question. There is no inequality types until now. So after 2011, before 2011, on 2002 and 2003, we had the inequality type. The equation type we had, I think, 2001 or maybe yes. And before that, we had many questions, the equation type question. Equation type question, you have to think and do. Right? Okay, so we'll start with the first question. Example, write down the example, mathematical induction. The first example, okay? That's it. The very important thing is you shouldn't miss any classes because the classes at the time we can say many things, right? It's not only these things we are related to many things. So the last relative velocity class we learned that how to do using the chord theorem. Okay, chord theorem, so relative in a circle. And in 2014, but how we use the other way around, right? So we learned that divider compound. So there are many things. So sometimes I may do the same thing, or I may do the different thing. So that's up to the mood I am having at that time. Okay. So okay. So the example. So example. The first example ever. So what we teach to the students. The first example under the series type. So we are going for the series type first. Ever. This is the first example. Up to n, that is n by 2. There is a statement. There is a statement. Series type. So this can be given in another way, like this: sigma r from 1 to n by 2 into n plus 1. So if they gave in this way, what we have to do, and if they give in this form, what we have to do, we will learn. Okay, right? Okay. So the first one, this is, but unfortunately or fortunately, in 2012 paper, they asked the same question, this question. So most of the students they have done, because this is the basic, this is the first example we do under the mathematical induction. Okay. So what they say, so we will understand what the mathematical induction now. So the one person came up with, okay, so this is true for all the positive integers. All the positive integers. That is a very important keyword. So this is true for all the positive integers. One person said this is true for all the positive integers. So then we have to prove that whether it's true or not using the mathematical induction. So what we do, first of all, this is a statement of first of all, immediately we have to do for n equals 1, we have to check. So they say this is positive integers, right? This is true for positive integers, z plus. So sometimes they may start with n greater than or equal to 0 in some cases, not for this one, any other one. So in that case, you have to put, if they mention the 0, then you have to start with the 0. That's very important. Okay. So that is very important. Okay. Okay. So we come back to this. So here, 1, always 1. Right. So the 1, I put 1. For n equals 1, I am going to check whether this is correct. So I'll check the LHS. When n equals 1, I am having 1. So we'll check the RHS. For n equals 1, half, we are put 10. So otherwise, they will, that is also 1. So you have to say that LHS equals RHS. First of all. Then you have to say that this is true for n is equals to 1. This is true for n is equals to 1. Write down, this is the first one. Up to here, you have to write. Okay, so write down. So the process isn't finished. Isn't finished, well, we have to go through that. Okay. First, we have to show this is true for n equals 1. So for n equals 1, this LHS is 1 here. RHS is 1. So LHS equals RHS. LHS equals RHS. So this is true for n equals 1. Okay. So then I erase this again. So quickly write it. Right. So the process is very important. Right. So quickly write it. Shall I write? Shall I erase this? Yes. So after that, what we have to do? After that we have to assume that this is true for n equals k. Okay, so many students, some students, they take n equals p. Okay, no problem. According to the question, you can say. So most of the time, I take n equals k because you will have the confusion in this 2006 past paper because they use the p in the question. So if you say p also, that will there will be a collision, right? So that's why I use the k. If they use the k in the question, then I use the p, right? Right. So that is a. I'm not going. Okay, so this is true for n equals k. We have to assume that let this is true for n equals k. Write down this. Let, you can't say that this is true for n equals k. You have to say let this is true for n equals to k. That means we are considering this is true for n equals to k. So that means we are pushing the k book. We are pushing the k book. K book isn't falling naturally. We are pushing. So we have to say that we are pushing. That's why let this is true for n equals to k. Okay, so then you have to show that this is true for n equals to k plus 1 also. That you have to show. You shouldn't push that to k plus 1 also. You can't push the k plus k book and k plus 1 book and you can't say this is consecutive falling. No, not like that. So you only push the k, then because of that k plus 1 should fall. Right. So then let this is true for n equal k. So then okay, we'll put there up to k that equals, so k by 2 into k plus 1. Okay. So let this is true for n equals to k means 1 plus 2k, k by 2 into k plus 1. So that's it. Then what we have to show, that is the thing. So we have to show that this is true for k plus 1 also. If it's true for k plus 1, what we have to write? So take a rough paper. If you take a rough paper and write, if this is true for k plus 1, what I will write? Then I will write 1 plus 2 plus up to. Instead of k, I put k plus 1. So instead of k, I put k plus 1. Right? That is k plus 2 in that case. Okay. I put k plus 1 for n, or k plus 1 for k. Right? So that means I have to show this from this. I have to derive this from this. That is very, very important. Okay. I have to derive this from this. Understood? So I rewrite again, some students unable to see that. Again, I'll write it. So I took, this is true for n equals to k. I took it. But I have to show what? I have to show this is true for n equals k plus 1. That means I have to derive that from here. So what I have to show? What I have to show is put k plus 1 for k and c, or n and c. 1 plus 2 up to 3. Instead of n, you put k plus 1. So that equals k plus 1 by 2 into k plus 1 plus 1. See, again, I'm having that problem. See, I'll rewrite. So 1 plus 2 up to k plus 1. Okay. Instead of k, n I put k plus 1. Okay. That equals, instead of k plus 1, k plus 1 plus 1. Okay, so later I can simplify that. So I have to show this, right? I have to derive from this. Okay, how to do that? So you have to write that on the rough paper. Okay, so always you have to think about this, how to show this. Right, I'll tell you the technique. The technique is, Some students they write n equal k plus 1 also. Poor, poor understanding. So you write k equals n equals k. Okay, that is you let this is true no. So you can take it. Some others they write k n equals k plus 1 also. That means you are pushing the k both and k plus 1 also. You say this is both are falling. Not like that. But so nowadays they are accepting if you write that, but that is a meaning that you are substituting there. So don't show again same thing. So don't put a k plus 1 for n, and they don't show that like that. Okay, you have to show both statement at the same time. Some students they think okay they put here, but they can simplify and show not like that. So you have to derive this from here. Derive this means not putting k plus 1 for n. So we omit that. But in paper schemes, they don't, still they are not strict with this because they know students are like that. Even they mistakenly they put k plus 1. Okay, no, don't worry about that one. Okay, so don't write n equals k plus 1. So you can write when it's coming to the division type question. When it's types the division type question. So division type question you can write. Okay, so I will explain in that case. Series type question, what you have to do after identifying this is series type question, you have to add the next term both sides. This is the key. If you are end up with any series type question, what you have to do is you have to add the next term to the process, right? To the statement, right? So then that is the best way to derive. So what we have to do is, this is a series type question we understood. So what I have to do, I'm going to write add both sides the next term. So what is the next term? K is there. So k plus. So I say add. So write down add k plus 1 to both sides. Okay, so what is the key? If you identify this is series type question, you have to add the next term. Okay, right. So I line above k plus 1. That is not line, that is a bracket actually. So that is another kind of bracket. So I can put bracket like this. So say there is a k plus 1 is a one thing. So that's it. So since there is a bracket, so better to do that line. Put the line. That means I'm showing that instead of k, now k plus 1 is sitting. See? Instead of k, now k plus 1 is sitting. So that means this is true for k plus 1 also. Understood? Okay. Right. So that is okay. Right. So we put the line. That is another kind of bracket. Okay. So there are brackets. There are open brackets. There are curly brackets. There are closed brackets. And if you put line also, that is we consider as a bracket. Right. Okay. Line on the top. So now add k plus 1 to both sides. So then I'll be getting 1 plus 2 plus 3 plus k plus, I'm going to write in red. Okay, so k plus 1 is added. Okay, I can write like by putting my brackets, or I can write by putting the k plus 1 bracket like this. Okay, that equals that equals I erase this one because I need the space. So here I'm having k by 2 into k plus 1 plus I'm writing this k plus 1. Okay. So what I can do is take the k plus 1 as a comment. So if you don't like, just write k plus 1. If you want to put a bracket, just put it, no problem. So put it. Okay. So now you have to simplify this. Yeah, here this part is over. See here? So instead of k, you put k plus 1. That is there, right? So don't put k plus 1. Add k plus 1. Okay. Don't put k plus 1 for n. Add k plus 1 both sides. So that's why you got this 1 to k plus 1. Now we have to show that, you have to simplify this, and we have to show that that is k plus 1 by 2 into k plus 1 plus 1. Right? You have to simplify this and show this is equal to this. So we will do that. When you simplify, what we have to do, you have to take the common thing out. So that is must. What's the common thing? And if you have any number down, you can take it out. So if 2 is there, you take it out. So it's k, this is k plus 2. So finally I can write this is k plus 1 by 2. K plus 2, you can write k plus 1 plus 1. Why you are writing? Because then only I can compare. Okay, so instead of k, you are putting k plus 1. It seems to be instead of k, k plus 1 is there. Okay, so that means this is true for k plus 1 also. So that is the end. After that, you have to write a small paragraph. So please write down, then I will tell the paragraph what you have to write. Always you have to copy that paragraph under after any mathematical induction. So don't only write the paragraph and come. First you have to do, then only you have to write the paragraph, right? So right up to here. Okay. So mathematical induction, I erase this. This is series type question. Series type question, you have to add the next term both sides. Series type question, you have to add the next term both sides. So what you have to write down after this, I'll tell you, please write down. So this is the common paragraph you can write under any kind of mathematical induction question. You must, otherwise they will reduce 5 marks. Okay. If you don't write the paragraph, they will reduce 5 marks. Since if you just only write the paragraph and come, they won't give the marks. You have to do this and then only you have to do the write the paragraph, right? So let's see things. Guys, write down the paragraph. The paragraph is if this true for n equals k, this is true for n equals k plus 1. If this is true for n equals k, this is true for n equals k plus 1. Then this is true for n equals k plus 1. But this is true for n equals 1. But this is true for n equals 1 also. Then we prove that consecutive books are falling and the first book also falls. Then the entire will fall. So then here you have to write, if this is true for n equals to k, this is true for n equals k plus 1. But this is true for n equals 1. So, right? Okay. So this is very important. By mathematical induction. These words are very important. Right? By mathematical induction, for all the values, all the integers, all the positive integers of n, all the positive integers of n. Okay? Positive integers of n. So by mathematical induction, for all the positive integers of n, this is true. So you have to write this statement. So very important keywords. If you can buy hard or you can memorize this and you can write, or you can. The main thing is this, underline this. Mathematical induction, that word should be there for all the positive integers of n. That word should be there. So these are the keywords. If you are not writing without, if you are writing without these words, they won't give marks. That's it. For by the mathematical induction and for all the positive integers of n. This is true. Okay. Is it clear? Right. So is it clear? Okay. So this is hopefully this is clear. So I erase this one. This is the question. Okay. So I am going to give now the question another one. So you can, this is series type. So we will do all the series type questions now. So now we go to the 1 squared plus 2 squared plus 3 squared. So second one, we have to prove. This is not example, we give exercise. Okay, exercise. Example, one example enough under the series. This is n squared. So one person came up with this. Okay, this is n by 6 into n plus 1 into 2n plus 1. Okay, so you have to prove this using the mathematical induction. You have to prove this one and tell you another question also. That is second one. This is second, first exercise. The second exercise is 1 cube, 2 cube, 3 cube, up to n cube. That will be n squared by 4 into n plus 1 all things squared. Or n by 2 into n plus 1 all things squared. Or n squared by 4 into n plus 1 all things squared. Okay, guys, I think these are homework, right? So I'm not going to waste the time right now here. So I'm going to conclude the class. Okay. So these are the homeworks, and then we will do some others under the series type questions. Now you can do the first part questions. 2011 is, I think, it's a division type. 2012 is a series type. 2013 is the series type. I think no, division or series. Only those things. So if it's division, just leave it. If it's series type, please do it. Okay, so I'll tell you one more thing. Okay, one more thing. So before we conclude the class, that is, so if they give something like this, what happens? Sigma r. So that is the previous one, n. That is n by 2 into n plus 1. So what you do? So if they give in the sigma rotation, no problem. So first we have to assume that this is true for n equals to k. Okay, that is k, k, k. Okay, and then you have to say you have n equals 1 also. That's not a problem. No, that's okay. K plus 1 means keep this, and add the next term, that is k plus 1 to both sides. So hereafter, so here you can simplify as usual. This one, this side, after writing this, you can add up 1 to r k plus 1 instead of k plus 1. Is it clear? So if they say 1 to n, then instead of n, you are having k plus 1. Okay. So then you can simplify that. So if they give sigma, that's easy, because only thing is you have to add the next term and add up it in the top. Okay, so that's it. So we will do that next class, and probably we can start the division type, and also we can go through many questions in under the series type. So division and series type, only two types are coming to you. Okay, right. So if possible, yeah, right. I will arrange it. Okay, is it clear? So only two types are coming to you in this syllabus, not syllabus, in these days, okay? So they are able to put the other two types also. So we will learn all four types. Okay, bye. See you guys. The last class recordings, if you want that relative velocity, and message me. Okay. Okay. Bye.